Hi guys, welcome back. We're picking up right where we left off and learning gas laws. We're learning two more tonight, and we're going to start with one called Gay-Lussac's law. And so the relationship here is that when the temperature of a gas increases, the pressure should increase as well. So the relationship we're looking at is between temperature and pressure. So they're directly related. And essentially, if the temperature of the gas were to decrease, then the pressure should also decrease. Now for this one, please note that the temperature, if you're doing a recording or a calculation, should always be in kelvins. So most of the time you're given a temperature reading in degrees Celsius, you would first need to convert to degrees Kelvin before moving forward with the calculation. But more about that when we get there. Okay, so let's take a look. So assuming we have the exact same conditions in both of these meaning we have the exact same quantity of gas and the exact same volume. If I increase the temperature on this particular gas, then the collisions that are happening inside start to increase, which then increases the pressure. Okay. All right, so let's look at the calculations. So we can use this law to calculate a change in pressure after a temperature increase or decrease as long as, and I already said this, as long as the volume and the amount of gas remain constant. And so this is the equation that we'll use. P1 over T1 is equal to P2 over T2, where P1 is the initial pressure, T1 is the initial temperature, P2 is the final pressure, and T2 is the final temperature. Okay, so here's a little example here. So determine the pressure change when a constant volume of gas at 1 atm is heated from 20 degrees Celsius to 30 degrees Celsius. So we're given a P1 of 1 atm, we're giving a T1 of 20 degrees Celsius, and a P2 of 30, or a T2, sorry, of 30 degrees Celsius, so we need to find our P2. Now remember I said the first thing we need to do is convert those degrees Celsius into kelvins, and we do that by adding 273. And if you didn't know that that's how you did that, then you can use your reference sheet that was given to you or that you can access on your Canvas page. So again, we're faced with two fractions. So in order to set this up to isolate one of our variables, we'll cross multiply here. So P1 times T2 will be set equal to P2 times T1. Where we're trying to isolate P2, so we'll divide both sides by T1 and get P2 on its own. We'll plug in our variables with our new Kelvin readings instead of Celsius variables, and once we plug that in and we look at our sig figs, we're left with 1.03 atms. Okay, so we're at a U try, so if you didn't get a piece of paper out at the beginning, go ahead and get a piece of paper out now, and then as soon as you get to the next slide, there'll be an answer. So the gas in an aerosol can is under a pressure of 3 atm at a temperature of 25 degrees Celsius. It is dangerous to dispose of an aerosol can by incineration. What would the pressure in the aerosol can be at a temperature of 845 degrees Celsius? Okay, go ahead and flip to the next slide when you're ready. All right, here we are. So the gas in an aerosol can is at a pressure of P1 here, 3 atm, at a temperature of T1, 25 degrees Celsius. What would the new pressure be, P2, so that's what we're searching for, if the temperature was increased to or heated to 845 degrees Celsius? Remember the first thing we said, this needs to be in kelvins, so we need to add 273 to both of these numbers, and we'll get our new Kelvin variables here. We will rearrange this equation so that we are solving for P2 by isolating it and dividing both sides by T1. We'll plug in our variables, making sure that we include units, and including sig figs, we get an answer of 11.3 atms. Okay, and that's it for Gay-Lussac's law. Now we're going to look at a new one, the combined gas law. So the combined gas law is an interesting one because prior to this, we'd only really been dealing with two variables, pressure and temperature, volume and temperature. Now with this, we are going to be looking at three variables. We are going to be looking at pressure, temperature, and volume all being manipulated in one. And basically what the combined gas law says is that volume is inversely proportional to pressure, but it is directly directly proportional to temperature. So if volume is inversely related to pressure, if the volume increases, then the pressure decreases. But if the volume is proportional to temperature, if volume increases, then so will temperature. Again, for this one, temperature should always be in kelvins. And then we used this law when we're changing two variables at once. So when both pressure and temperature are being changed, we use the combined gas law. In our previous examples, only one variable is being manipulated. Here, two variables are being manipulated. And in order for you to use this gas law, the amount of gas must always remain constant. Okay, so here's the equation. So if a sample of gas is under two different sets of conditions, we're going to use this combined gas law. And it's P1 times V1 over T1 equals P2 times V2 over T2. And by now you know what these variables stand for. Initial pressure, volume, and temperature versus final pressure, volume, and temperature. So let's take a look at how to calculate this. So a cylinder with a movable piston has an initial volume of 3.65 liters and is carried up a mountain. The pressure at the bottom of the mountain is 755 mmHg and the temperature is 302 Kelvin. Now the pressure at the top of the mountain is 687 mmHg and the temperature is 291 Kelvin. What is the volume at the cylinder at the top of the mountain? So we have a cylinder and it has conditions. It has a pressure and a volume and a temperature when it sits at the bottom of a mountain, and then it has a new pressure, volume, and temperature as soon as it's carried to the top of the mountain. Now what they're asking you to do here is determine what the pressure will be, what the volume will be at the top of the mountain. So the bottom of the mountain is going to be your initial readings, and the top of the mountain is going to be your final readings. So based on what they told us, our initial pressure was 755 mmHg. Our initial volume was 3.65 liters, and the initial temperature was 302 Kelvin. Once we got to the top of the mountain, the pressure changed to 687 mmHg, and the temperature changed to 291 Kelvin. And now we're solving for V2. And we will rearrange this equation just like we did in the previous one, cross multiplying and getting rid of or eliminating our variable and eliminating our dividing by the variable that we need to isolate by. So in this case, we have P1 times V1 times T2 set equal to P2 times V2 over T1. And because we're trying to isolate V2, we will divide both sides by P2 and T1 so that we are left with this final equation that solves for V2. And then we can plug our variables in. And these were already in kelvins, so we didn't have to worry about that. And our final answer with sig figs is 3.87 liters. Now you actually don't have to, I should clarify here, on this one you don't have to have an answer in Kelvin. Celsius is acceptable. So keep that in mind when you're doing this one. So we're at U-try number 4. A sample of a gas has an initial volume of 158 milliliters at a pressure of 735 mmHg and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 milliliters and heated to a temperature of 85 degrees Celsius, what is its final pressure in mmHg? So pause here and try to solve this on your own, and when you move on, the answer will be on the next slide. Okay, so here are the answers. I went ahead and filled in all of your variables for you. We are solving for P2 here, so we need to ensure that we isolate P2, and you'll see that I rewrote the equation for you. P1 V1 T2 over V2 T1 is set equal to P2, where I plug in all of our variables, and I get an answer of 1.25 times 10 to the third mmHg. When I'm reading these problems, by the way, I like to go through and highlight and write out what my V1, V2, P1, T2 are. And I also always will do this because I like to keep my thoughts organized, especially when you're dealing with this many variables. So I highly recommend that you do this as well. Even for some of the other ones where we're only manipulating 2 variables instead of 3, I find this easier. All right, guys, thanks. Let me know if you have any questions, and we'll talk more in class.